Hey, hello everybody. Welcome back to another episode of Max on Color. And I'm really glad that you can make it today here, folks. And good morning to you guys who are joining us today from the Pacific time, and good evening to you guys who are joining us from the European time zone. Hope you're all doing well. And how are you guys doing?
Good, man.
Awesome.
And
Thanks
as you
for
see
asking.
today,
How are
we
you?
are. I'm great, man. And as you see today, we are joined by our good friend Cullen Kelly. Welcome back, Cullen.
Thank you very much. I'm fired up to be here.
And today he's a man on the missions because he wants to share his deep knowledge about color management, particularly ACES. We're going to demystify ACES together. So if you've attended the previous session with Cullen, you know that we've gone through a meticulous detail about the concept of color management and ACES, which in my opinion, one of the best sessions I ever watched about ACES online. And
Yes.
thank you for that, Cullen. Thank you for sharing that with us.
My pleasure.
And if you
Max,
guys
should we also point out that we recorded that last session and that it's on the
exactly
Maxon Training Team YouTube? Because
exactly that's
worth
exactly what
checking
I'm
out.
going to do, because
Sorry,
if
interrupt
you
you.
miss that recording, you can simply go to the our YouTube channel, and under the name Max on Training Team, and if you go to the playlist, you'll find Max on Color. Simply open that, and then you'll see sessions with Cullen, part one, exactly there, demystifying aces with Cullen Kelly. So make sure to check that one, and I think that will be a really a nice foundations for this sessions as well. So before I hand out the floor to Cullen, let me just do a small how do you call it, housekeeping, if you guys know don't mind me to do that. And by the way, you can get a free T-shirt today, and if you want to, you can go to this link, um, and I'll share the link in the chat. And how do you call it? The code for today is the one that you can see in your screen. So, for example, if I enter the code, it's particle magic, by the way, all capital. You can order one of this T-shirt free of charge, of course, and yeah, but the code can be only used once, so one T-shirt per person, please. So this is like literally our thank you to you guys, our way to say thank you to you guys for always showing up in Maxon online events. And if you want to check the upcoming events, you can go to maxon.net/events, and you'll see that tomorrow Hashi and Seth will be back with another episode of VFX and Jill. And next Monday, I think Chad will start a new series on demystifying post productions. It is already ongoing, right, Chad? And it's all
Correct.
about
This is
particles.
week 2. This is on X Particles, if you're familiar with that. And Bob Wormsley from X Particles from Insidium is going to be joining us and talking about X Particles. So it should be really awesome.
Amazing, amazing. So before I continue rambling on and on and on and drive you guys mad, let me just hand out the floor to Cullen, and let us enjoy what Cullen will show us today. Cullen, the floor is yours, man. Take it away.
Okay. Hey, everybody. Good morning, all. Any of my YouTube fam out there? Anybody coming over from my channel to hang out with Max on this morning? I hope so. I put out a blast on the channel because this is a conversation that I love to have and that we don't often get to have in the format we're going to do today, which is a bit longer of a sort of portion size. And we're getting to do, of course, a second part today, building on the foundation that we covered in part one. So really what I want to do is just continue sort of deepening our understanding of ACES and where it's come from and where it's going, where it's currently at as well. Now that we understand the basics of color management, we understand the basics of ACES, I just want to explore sort of the state of the art of this system, which is the most popular color management framework for motion images in the world. We all should, if we're touching that motion imaging at all and we're working with color management, which we should be, we could all stand to better understand some of the nuance that comes along with this system. So where to begin? what do we think, Max? We talked about, so we sort of left off, you know, I think at the end of our last conversation with a good understanding of the overall picture. And I think like today it might be good to start by talking about like our AP1 primaries. What do you think about that?
Yeah, let's do this.
All right, so let's see if I can figure out how to share a screen. I know what I'm doing. I know what things are. Okay, there's that. Oh, I have to enable some permissions. My computer really doesn't want to let any application share my screen. Okay, here we go.
We've all been there, man. Feel your pain.
Yeah, there's always something, right? Are you guys seeing an image yet?
Yeah, we're seeing.
Yes.
your
See exactly what you have in your masterclass normally.
Yep. This is my stock array, isn't it?
Yeah,
All right,
that
so.
is my secret plot to push your masterclass a little bit.
Yeah. If anybody has 18 hours to spare for one part or 36 hours to spare for two parts of my creative color science classes, then the recordings are available, and you're probably a little sick in the head like me.
I'll
and
paste
Dr.
the link.
I know it's
I'll
great.
provide the link. I'll provide the link in the chat.
All right, so here's what we're going to talk about today, guys. Let's talk about something we can identify visually here. So right now, just in terms of sort of some basic context of what the heck we're all looking at right now. I don't care if you're a Resolve user or not. I don't care if you're a colorist or not. I'm going to walk you through what I'm doing here in a way that kind of makes sense to all of us. So we now, hopefully, if you've joined for part one of this conversation, we understand that ACES is just a standardized framework, a standardized pipeline for taking what the camera saw and turning it into what our display can show. So the two operative variables in that pipeline are, of course, what the camera saw, what was the camera, and then, of course, what is the display that we are mapping to. We need to plug in those variables. That's what we do whenever we are setting up an ACES color management environment. The way I have that set up today here in Resolve is one of a couple ways that I could set it up, but I'm doing it explicitly in nodes here in Resolve. And here's my flow. I'm going from my Alexa source into the ACES CCT working space that we talked about in part one. And then I'm going to do all of my grading here in between, which right now is nothing at all. I'm just doing the pipeline. And then here at the tail side of it, we are going out to Rec 709. I'm actually going to skip over what we're looking at there for now. We'll come back to that. And we're going to go out to Rec 709, like so. So this is our overall pipeline. And every single shot in this timeline is getting this same treatment that I just described. Let's go over here to shot number 10. There's a reason that I like to keep this shot handy in my timeline. Let's take a look at something here. I'm going to make this a little bit bigger for all of us. Everybody see that? For all of y'all watching, does this look familiar? Is this something that you've seen perhaps while working with ACES? The dreaded cyan tearing?
Yes, and I'm grateful that we talk about it.
Yeah. Now, it's funny. I'm really glad to be talking about this today because I was an early adopter of ACES, and I used to get this all the time because I was an early adopter of ACES working with like large color gamut source material, which is sort of the perfect recipe for getting this type of thing. Anytime you have a, like a professional quality camera and you have any kind of rich cyan or blue in the image, that's generally where you're going to see this. So I was getting it all the time, and I actually didn't understand why I was getting it. And when I would ask people, I would kind of get a bunch of like vague double talk that wouldn't really help me understand what I needed to do any better. So what I want to do before we talk about, well, how can we solve this problem? I want to start by understanding what the problem is. Like, why is this happening? ACES is like the most prevalent standard for color management for motion imaging in the world, as we talked about, at least by my measure. So shouldn't it not do stuff like why am I seeing this? What's the problem here? Let's start by identifying that. I'm going to take a look at a CIE horseshoe diagram here that is showing us the primaries of the ACES color spaces, okay? We talked in our last session about the multiple color spaces that are associated with ACES. So there's not just one ACES color space. There's a master color space for ACES, which is itself called ACES. And that is a big fat gamut like we see here on the left, this big yellow triangle enclosing what we see here as the entire spectral locus. So this actually isn't a coincidence. This is the smallest triangle that the engineers who devised the standard were able to draw that would completely encompass this horseshoe being every color that we are capable of seeing. All right, so that's the idea here. This triangle is not an inch bigger than it needs to be to fulfill that mission of completely enclosing this horseshoe. Even though there are colors outside of that horseshoe within the triangle could not be any smaller and still get all the colors of the horseshoe contained inside of it. Make sense? So that's our ACES AP-0 standard. If I give you an ACES file for VFX exchange, for example, it's going to be AP-0 linear, meaning the large primary set and a linear response or a linear tone curve. Let's now look over here at the right. We're going to look at the ACES AP-1 primary set or the ACES AP-1 gamut. This is the primary set. This is the color space. This is the gamut associated with the ACES CCT working space that we're operating inside of here inside of Resolve right now, that any vanilla ACES pipeline for color grading is going to use. You're either going to be in ACES CCT or far less commonly in ACES CC. Either way, your primaries, your gamut is not this big giant triangle, but this triangle here. And if you notice, this gamut itself is also not arbitrarily drawn. It's not a coincidence. It aligns very, very tightly with Rec 2020. Okay, so that was the sort of concept behind the ACES AP1 primary set. Now, what's interesting that we don't see graphed here in this chart is if we think about the primary set for the source that I have right here, that right now this is an Arri Alexa image, that primary set actually has values that live outside of this triangle. That's why this happens, okay? To put it even more sort of specifically, what actually happens is when we perform our transformation from our Alexa source into ACES CCT, so we're basically like, to get really granular for a minute, if you don't follow all this, that's okay, but if you're a geek, maybe you'll enjoy it. What ACES is actually doing under the hood here is the following. It's taking an Alexa Arri-wide gamut log C input image. It is first linearizing that log curve or decoding that log curve back to linear. It's then applying a 3x3 matrix to transform us from Arri-wide gamut into the ACES AP1 gamut. And it's right there that the problem arises. When we perform that matrix operation, which is basically just a series of multiplications, the product of some of those multiplications ends up being a negative number. The negative number is what creates this tearing, what creates these problems, and the negative number arises from the fact that this is smaller than the triangle that describes the original color space of our source image. And you can understand why this is only going to arise in certain cases. This is basically only going to arise with sources which have a color space whose triangle, to put it simply, is larger than this triangle, and with images that have values in them that actually hit those boundaries, that hit those regions outside of the ACES AP1 gamut. So that's why it's something that can kind of sneak past us without our noticing a lot of the time, because this is not the only shot in Arri, right? Pretty much all these shots, I think I might have a couple red shots here at the beginning, but these are all Arri, and I'm not seeing any tearing in most of these. These all look fine. That's because even though they are in Arri-wide gamut, they don't actually happen to have any pixels that are living in that area of the triangle which is outside of the AP1 primary set, the AP1 triangle, okay? So that is the issue in a nutshell. That's why this happens. And when I finally understood this, when I finally figured this out years ago, I was like, oh, okay, I see. That makes perfect sense. Now I know why it's happening. The best solution that was out there for a long time with ACES, when you could ask the Academy directly, and the solution that they would give you would be not this LMT, but let me go to my root level folder here. This guy right here, LMT neon suppression. And this is sort of the prescribed solve. This, by the way, is a 3x3 matrix. And you would apply it to your image and hope that it helps. And what we often found is that it didn't help, because a 3x3 matrix is really not what's needed here. A 3x3 matrix created the problem in the first place, and it's unlikely to solve it unless we do something else undesirable to the image. So this was the status quo. This was the best we could get until quite recently with ACES, right up through ACES 1.2. This was like the prescribed solution. If you reached out to anyone on the ACES committee and said, hey, I'm getting this problem, what do you think I should do? They would tell you either to sort of manually implement your own solution, which I've actually done videos about on YouTube prior to ACES 1.3, or they would say, try this neon suppression LMT as a 3x3 matrix and see if it helps, and it rarely would. That's changed with ACES 1.3. So let's take a look at our options now within ACES 1.3. So right now, let me turn this gallery off so we got a slightly bigger image again. And I'm going to go back to... Yeah,
can I
go ahead.
interrupt you with a couple of questions that you don't need to answer right now, but maybe just
course.
as they come up? I'm not sure what a 3x3 matrix is. I don't know if that's something that can be quickly, easily explained, or if that's really helpful here.
Yeah.
And the other thing too is that I don't know about the ACES, CC, CG, CCT, all those, the difference of those, and like that feels like something to be discussed at a different time. But if that comes up at some point today, I would love to know if there's a quick explanation for those.
Absolutely. In fact, I think we can at least do a quick lap through both of those things right now, and then maybe return to them in more detail later, as you suggested. So let's talk about 3x3 matrices first. So we're all familiar with like a gain wheel inside of Resolve here, where it's, you know, if we think about the actual math of it, all we're actually doing is multiplying our image by this factor. So that's why our gain is at 1 by default, because anything multiplied by 1 is itself. If we multiply it by a value greater than 1, we get brighter. If we multiply it by a value less than 1, we get darker, right? That's a gain operation, super common, really basic thing that we do in image manipulation. If we look at the RGB mixer here inside of Resolve, this is actually a really handy visual representation of what a matrix does. This RGB mixer is just applying a matrix per the user's input parameters here in the sliders. So all an RGB mixer is going to do is, in contrast to my primaries bars here, where all I can do is control, okay, how much red is in my image, how much green is in my image, how much blue is in my image. Another way of putting this would be, how strong is how much red is in my red channel, how much green is in my green channel, and how much blue is in my blue channel, okay? Let's go over to the RGB mixer and look at how it expands on that feature set. So fundamentally, it's the same thing. Those 3 bars that we were looking at before, those correspond to this bar, and that bar. The only difference with an RGB mixer is, in addition to saying, for example, how much red is in my red channel, I can also assign a certain amount of green into my red channel. I can also add or subtract a certain amount of blue. Same thing with my green channel, same thing with my blue channel. This is useful in a variety of contexts, but the main application for a 3x3 matrix, which is what we're looking at here, that's 3x3 because we have 3 terms for 3 channels, okay? The main utility of that, the way we most commonly use this in image science, is to move between color spaces. So remember we said a moment ago, when we are moving from the area-wide gamut to the AP1 primary set, we do that in a linear tone curve, and we do it by entering some particular values into here. So if I wanted to look them up, I could actually do that transform from area-wide gamut to AP1 right here on my RGB mixer. All I'd have to do is make sure I'm in linear and that I am taking the math that I could easily calculate and punching it in as values into each of these fields. Okay, so that's a 3x3 matrix.
Yeah.
Go ahead.
Can I just interject? Chad, when you think about the 3 points that create a gamut, the 3 primaries, and when you want to move one of these down into the triangle, then you could use all 3 to define where the new point is. And that is exactly what he did with the 3 sliders for 1. So when you have a triangle and you want to change the triangle, you have to define, exactly, thank you for the picture. You have to define the new position with the other three primaries.
That's exactly right. It kind of goes back to, like pretty fundamental, like, function plotting or plotting a graph. You're like, oh, if I want to move this straight down or down and to the right, what factors do I need to multiply it by? How do I get those coordinates? And you can perform simple multiplication to do that.
Exactly. And it's always in linear. When you have a gamma-based image, it will not work. Is that correct?
That's exactly. There are rare exceptions, but very rare. For normal technical color mapping, you're going to be in a linear domain. It just works. That's the way to change to change the response properly.
Thank you.
So
thank you so much.
Yeah, no, I'm really glad you asked about that, because that is kind of a very fundamental thing that is super helpful to have a bit of a better grasp on. But that's the essence of an RGB, or a 3x3 matrix, I should say. And again, like this can probably now add a little bit of helpful information to the observation we made a moment ago about the results of a 3x3 matrix operation turning a number negative, right? Because you can imagine, like, with the right combination of terms here, I could turn a number that started positive when it was fed into I could turn my input red negative with the output red by turning these sliders into a particular position, right? And it's those negative values that become a problem. And actually, just before I continue and show us the solution to the issue, it's worth observing the problem. The root of the problem happens at this transform, like we talked about. So right now, we're starting area log C, and we're moving into the AP1 primary set here, okay? The root of the problem is here. However, the actual breakage doesn't happen until a little bit later. It's only when we feed those negative values into the next link in the chain that bad stuff happens, because this right here wants positive values. It doesn't want negative values, okay? So it's actually an interesting distinction to make. The symptom, or excuse me, the root of the problem is here, but the actual manifestation of the problem doesn't happen until we get a little bit further down the chain, like so. All right? So with that background in place, let's now talk about the rather elegant solution that was implemented in ACES 1.3 for dealing with this. And, like, this is something that I talk about all the time, guys. If we think about, well, why did this happen? Why is this a thing in the first place? And what's the best way to address it? This happened because ACES was the very first color management framework on the scene. That's a really good thing in many respects, because there's some maturity there, there's some evolution that's taken place there, there's been some wide-scale adoption that requires time in order to happen. There's a lot of benefit to being the first player on the field, to being the first, leader in a space. One of the downsides is that when this standard was being drafted, now whatever, 15 plus years ago, there simply wasn't enough forethought about the gamut and the expansive gamuts that we were going to end up having commonly available to us in our cameras. So there just wasn't enough accounting for contexts like this one, because this was devised so long ago. And the challenge is that ACES, like most organisms, can really only evolve forward. I've heard this analogy before, just to make a comparison. If you wanted to optimize the city of New York, if you wanted to completely optimize all of its infrastructure, the subways, the way trash gets transported, running water, electricity, sewage, the whole thing, you could increase the efficiency of New York City's infrastructure like 1,000-fold if you could shut down the city of New York. And if nobody had to go to work, and nobody had to have running water or air or heat or anything else that the city needs to survive. But that's not the way the city of New York works. It's an organism, right? So it has to evolve forward. It has to evolve while it's functioning. And that's the same thing with ACES here. If you could take that knowledge that we now have, that like, hey, AP1 is actually kind of problematically small, you could go back to those engineers back when ACES was being devised and come up with a better standard. However, ACES is already out there. It's already in the wild. It's already on its feet. It's already evolving, and it can only evolve forward. You can't go backwards. So the ideal solution would be, oh, let's devise the AP1 primary set in a different way. But the only reasonable solution is to figure out how are we going to do a better job of this right here. That's the pivot for a working organism like ACES. And here's what they came up with. It's actually really cool. So I'm going to go to my ACES transform that I have set up here. And you can see up through ACES 1.2, these are my options. These are my only options. This is the only parameters available to me in terms of how are we going to make that journey from camera color space of Alexa into ACES CCT. This is all we got. Let's go to ACES 1.3. Now we've got this Gamut Compression option here. And if I hit this drop down and I just do the simple ACES reference Gamut Compress, let's watch that nasty torn Cyan. How about it?
Wow.
It fixes it. And it fixes it in a really elegant way. It simply maps that Cyan into the nearest available. The fundamental problem with that Cyan before is that it is a combination of too bright and too saturated for what the AP1 gamut can contain. So all this is doing is mapping that to the nearest reasonable value that is inside of the triangle. And in doing so, we are keeping the image from breaking apart like it was a moment ago. So that's the solve they came up with, and it's a really elegant solve. And I actually want to go a little bit under the hood and explore exactly how that works next here, but I think I'll pause for a minute and see if I should clarify or answer any questions before I go on. All good out there? Everyone's either completely following me or bored stiff and comatose.
There's one question
Great.
in the audience, Colin. I think Bear Geist is asking, is that, I think he's referring to AP0 color. Is the AP0 color space is a theoretical color space? Isn't that what the XYZ color space is actually doing?
That's right. That's a very good observation. And in fact, just like we observed the tight correlation between AP1 and Rec 2020 here, AP0 and XYZ are very, very close. Like if you look at, an XYZ to, we just learned about matrices a moment ago, or an AP0 to XYZ matrix, they're going to be very, very close. Those factors are going to be very, very small because they align quite tightly. So short answer to the question, yes, absolutely, very well observed. They're buddies. They're of a kind, AP0 and XYZ. And they are theoretical in the sense that we don't want these imaginary colors that it contains. However, we don't have a choice. If you tell me pick the 3 points that are that form the smallest triangle possible that completely contains this object, this is the best we can do, right? So we have these imaginary colors that we wish we didn't, but we don't really have a choice if we want to completely enclose the horseshoe, the spectral locus. Okay.
Alrighty. Thank you so much. I think that's
Yes,
it.
sir. Good deal. All right, so let's geek out for a minute here, guys. I think this is fascinating stuff to look at. Like, all right, that's great that this works, but I'd kind of love to know why it works. So let's turn this Gamut compressor off. Now, I'm also going to talk about something that I love about ACES, something that I think really makes ACES a compelling color management framework compared to almost any other that I could think about, is that it's open source and it's evolving in the public eye. It's evolving before us. So this is an issue that I've followed, as I said, since my very early days of adopting ACES. And I was watching with very keen interest when ACES formed one of their virtual working groups for this gamut mapping issue. And they had a really, really smart group of people come together to figure out, all right, how are we going to address this? If we're not going to expand the AP1 primary set, how are we going to address making a best fit of whatever the source may be into the AP1 primary set? And what we just looked at is the fruits of all their efforts. But what I thought would be kind of fun is to look at a little DCTL tool that they released along the way as they were working on these solutions. So this is actually the same exact algorithm that ended up finding its way into the implementation here inside of Resolve. But what's fun is we can get a little more insight into how this algorithm works because we have access to the parameters and to some sort of like viewing context that we don't in the final release version of Resolve, because they figure, probably correctly so, that most of us aren't crazy like you guys and me and actually interested in this stuff. They know that most people just want the right result, and all of us might want that right result, but we also kind of like the process of it all. So let's take a look at what's actually happening here. I'm going to start by hitting this overlay graph, and I want to walk you through what we're seeing here. So the first thing that's happening is we are taking whatever tone curve that we are operating in, and we are linearizing it for the same reason that we linearize prior to applying a 3x3 matrix. Linear light is the domain of real world light, right? It's the simplest form of light, or of tone curve, I should say, which is why we call it linear. So it's really the ideal place to do gamut transformation, like we did to get from area-wide gamut into AP1. It's also the ideal place to do gamut mapping, which is what we're doing here. Gamut mapping being the subjective exercise of figuring out how we're going to fit the colors of a larger gamut into the smaller container of a smaller gamut. So that's sort of like the task that we are assigned with here. And so you can envision that step one under the hood here is I'm being asked what my working space is so that I can convert into linear, do the stuff that's happening here on this curve, and then convert back into whatever my original metric was after having performed that operation, okay? And the first thing that you'll notice is I've got these thresholds, all right? These thresholds are C, M, and Y, right? That means cyan, magenta, and yellow. Now, why cyan, magenta, yellow? Why not red, green, and blue? Well, track with me for a second here. This will get a little mathy, but it's worth the ride. Remember how we talked a moment ago about the source of these problems being negative numbers, right? Let's think for a moment about, let's think about our blue channel. Let's think about a negative value in our blue channel. Well, what does that actually mean? How would we flip a blue channel upside down and then evaluate a negative value that rather than being less than 0, being greater than 1? Because that's really, if you look at this graph here, that's what we're doing. We've got this unity 1 line, and we're simply trying to figure out how to map things to fall into the proper range, right? How would we flip that around? Well, it's very easy to do, actually. If you have your blue channel, and if you're in a range of 0 to 1, you simply subtract blue from 1. And now you've flipped blue upside down. And what's blue upside down? What is an inversion of blue? Yellow, because these are our secondaries. So that's why we have C, M, and Y here, because they are the inverses of red, green, and blue. This C channel is being calculated as 1 minus red. Magenta is being calculated as 1 minus green, and yellow, as we just said, is being calculated as 1 minus blue. So now we have mathematically a sort of simpler problem to address, which is how do we compress values greater than 1 so that they fit inside a range of 1, as opposed to saying how do we grab values which have crashed through the floor and recover them back up into a positive state. The math is just a little bit easier here when we flip everything upside down. So that's kind of the sequence here, is we're going from our log into our linear, we're flipping everything upside down so that we have secondaries, cyan, magenta, yellow instead of red, green, and blue. We're doing our thing here, which we're going to explore further in just a moment. And then we're going backwards to where we came. So we're flipping cyan and magenta and yellow back to red, green, and blue. And then we're taking that linear metric that we're in and moving back into the ACES CCT working space. That's just sort of like the round trip of it all. If I did just the things that I just described, we would see no change in the image whatsoever. But what's important is getting into this state where you're in linear and you're operating on a cyan, a magenta, and a yellow channel. That's the domain. That's where we want to be applying this gamut mapping. So that's why we're going to all the trouble of traveling way into that realm to do a couple things and then come all the way back, because we want to be in that realm for the operations that we're performing, okay? And you can see all that is being done here is we are finding a way to take a line that once would have stood straight up, and we're saying, okay, how far into the core of the destination gamut do we want to compress everything? Okay, so that's all in the world that we are doing, is we are looking at we've got a threshold here, which is basically saying, how much of a core do you want me to preserve of my target gamut? The further down into this I go, the less saturation I'm going to be able to keep. And the higher up I go, the harder of an angle I'm going to have. So you can see if I go all the way up to 1 over here and I zoom in, now my Cyan compression curve, it's really not much of a curve. It's kind of a straight line, right? It's kind of a you know, not a 90-degree angle, but it's got a very hard angle to it here. That's not a very gentle way to treat our image. So we want to get some softness in there, but not so much softness that we are eating into the very core of our destination gamut. We want to be able to preserve saturation a bit more than that. And then the other element here is we are simply asking how far into the region above 1 or below 0, however you want to think about it, how far into that region do you want me, the gamut mapping algorithm, to reach and try to recover and scoop values back into the fold, if that makes sense. So the lower I go with this, the less effort it's going to make to recover values. So like with it at 0, it's not making any effort at all. It's saying, oh, I'm going to reach 0% above my normal domain. And as I increase this, it's saying I'm going to reach further and further out into the range outside of 0 to 1 and grab those values and try to pull them back in. Again, there's a sweet spot here between going far enough that you're actually doing something, right? But you don't want to go too further than you need to, because again, you're going to lose saturation unnecessarily, okay? And it's the same exact exercise for your magenta and for your yellow, like so. And the last thing I'll point out here, if everyone's brains haven't exploded yet, it's a lot to bite off the first time, at least it was for me, is one of the things that I think is really smart about this gamut compressor is it is a closed and invertible function, okay? So if I want to, at some point down the line, actually invert what I've done that I just did so that I could get better functionality out of my ACES CCT working space, you know, right now these values match the reference implementation that we were looking at in our input. And if we look at inverting that, now it's going to look strange, but if I actually do back to back, let's do a copy of this. So the first one, we just do the reference implementation. And in the second one, we invert. Now, the graphs are going to look kind of weird, but if I look at the net of these two operations, I've got a net 0 round trip. That's actually a really big deal. Gamut mapping is very, very difficult to invert in most cases. So the fact that this virtual working group was able to come up with a simple, robust, effective algorithm for the challenge at hand and to make it invertible, that's a pretty big win. So that's some of the best work I've seen come out of ACES. And that's where it's at right now. That's how the AP1 primary set is being sort of massaged into functioning with the massive gamuts of modern day professional cameras.
Cullen, I have two quick questions. One, what is DCTL? And also the other one is just to wrap everything up, like make sure I understand. So like the horizontal line is the highlight limit of the destination. And so then like as you're adjusting like the overbrights, I guess you'd say, for each channel, you're kind of bringing into gamut and you're controlling how you want to bring those highlights into the gamut of the destination space. Is that right?
Yeah, that's exactly right on both counts. So essentially, you know, if first of all, a DCTL, that's Da Vinci Color Transform Language. It's just a way of directly applying math to pixels. So this is a great example of a DCTL. When this working group was saying, hey, should we do it like this or should we do it like that? Or a second coder was coming into the mix and saying, hey, I optimized this a little bit, see what you guys think. A DCTL is a great way to exchange those ideas without having to say, hey, Resolve, you need to incorporate this into your ACES framework. It's a much faster, you know, like I could code up a simple DCTL for you in 5 minutes and hand it off to you and you could see what I saw. So it's a very handy way of exchanging algorithms and you know, image processing, you know, like routines without having to do a bunch of compiling and you know, like release, you know, like debugging and things like that. And then regarding the question about the actual graph here, it's funny, to be honest with you, when I look at this, the intent is clearly that this horizontal line would represent a 1. However, I'm confident, just because I know how this algorithm works, that like in the reference implementation, we're going to be reaching, you know, like we should not be mostly in bounds, but fully in bounds. Now, well, I'm going to get ahead of myself and get overly complicated. Let's suffice it to say, yes, what this represents is actually not the max luminance, but the maximum saturation of our target gamut, which is AP1. So it's different than luminance. This is how colorful can a thing be before it breaks. So what we are doing here, as you said, is we're controlling the journey from this down into that, and kind of looking at what's the minimum that we need to do in order to get a favorable result without going any further, because as we saw, as we start to adjust things, like here's a great example where it's like, wow, we're definitely solving the issue, but we're losing a lot of color along the way, right? So that's kind of the idea there.
Can you take a word, or can you take a moment to explain the triangle that we have with AP1 and how all the colors get compressed, because they get not equally compressed along the triangle. They get more compressed on the shorter distance to the white point than to the outside points. It's like in 3D when you have a sphere from above and you squeeze just 3 sides to it.
Yeah, that's a really good image, actually. I mean, fundamentally, this is a great introduction to, you know, sort of the general challenges of gamut mapping. But what we're dealing with here is we want to figure out a way to compress, you know, if I'm here and I'm in this, this AP1 area, right? And I have a value that's here outside of the triangle. I could just do what's called gamut clipping, or like clipping style of gamut mapping, where I just say, hey, grab this, find the nearest point inside the triangle and shove it in there, right? That would work, but it's not going to produce terribly great looking images, at least on like a consistent, you know, like 24 frame a second, hundreds of shots type of basis. So instead of just saying, hey, grab anything outside and map it to the same exact point. So in other words, it might be outside by this much, or it might be outside by that much, but it's still going to map to a single point. What we're doing here is saying, we would like to preserve some of the variation between saturations that may have been different out here, but are still out. You're preserving it, so like there's still a distance between here and there. It's just less of a distance than we had initially. So we're compressing at the edges, and what this threshold is actually controlling is saying, how far into the triangle would you like me to eat, or would you like me to push in order to compress my values? Because if I take this all the way down to, let's see here, let me reset this again. You know, if I take my cyan threshold all the way down to 0, you can see that's a much mellower curve. And the way that I'm doing it is I'm saying, hey, you get to use the entire gamut. You've got all of this room to compress along, so you actually don't need to do as much compression because you have more space to occupy on the output side. However, as we've observed now a couple times, the saturation is going to suffer as a result. So you want to find a compromise between preserving some portion of your core, but also giving enough sort of shoe leather, if that makes sense, for the compression algorithm to do its thing. Because if you go to an extreme example, you get what we looked at a moment ago, where it's like, oh, cool, that's not eating into my core gamut at all. I'm getting a pure linear response inside of my gamut. However, I've got this really nasty right angle, which is not going to do. This is effectively no different than doing that clipping style of remapping I mentioned ago, where it's like, all right, any value above 1 is going to plot to the same horizontal value on the output side.
I have one follow-up question, if I may.
Yeah.
The discussion typically when you go into compositing and visual effects is you apply this to keep all values usable, not clipped, not what we see in the left upper corner at the moment.
Mm-hmm.
And then you have to decide, do you want to go back with invert to fill the AP-0 space? So anyone else who wants to work later can just use the data. Or, and I think there is no reglementation so far, how to document that you have applied already the color gamut, because if you do it over and over again, the image will suffer tremendously from my point of view.
Yes, you're absolutely right. And in fact, it's worth pointing out that, you know, when we talk about invertibility, that's sort of on a sliding scale. Like this is more invertible than like, you know, I have LUTs in my personal library whose sole function is to gamut map, right? Those LUTs rank very, very low on that spectrum of like highly invertible to, or of being like almost impossible to invert and like pretty easy to get a decent inversion of. Those LUTs rank really low on that scale. They're almost impossible to invert in a good way. This inversion method works pretty well, but it's a great point, Dr. Sassi. Like they are not, this is not a, it's not a true net zero round trip. If I do this 10 times, I'm going to start to degrade my image and I'm going to be subject to the actual bit depth of the image, because at a certain point, your values don't have to be identical in order for your imaging system to see them as identical, because you can only be as precise as whatever your bit depth is. So suffice it to say, it's a great point that like going through this and then inverting it is something you don't want to do more than once or any more than you need to. And I would agree that you know, like having some sort of documentation in place for when and where you know, such compression takes place is really necessary, or at the very least being mindful of any place that you compress your image. Like this is a bit of a tangent, but I'll put it this way just because I think this may be more comfortable for many of us. When I think in my like normal everyday role as just a colorist making images look good, I think a lot about curves in the realm of a tone, of just like mapping from scene space to display space. And I'm very mindful of how many places in my pipeline I'm doing a nonlinear compression like this. We need this, it's absolutely necessary. There's no way I'm gonna get a great image without being able to compress things nonlinearly. However, I don't wanna do 8 different points of nonlinear compression in my pipeline. That actually doesn't help my image and it just starts to kind of beat up on it. So I would say the same thing is true here on the gamut mapping or on the saturation side. We wanna be mindful of you know, like how many times we are applying compression, and certainly how many times we are applying and subsequently inverting compression, because it is not a lossless proposition.
Yes, and please let me add that we do not talk only about discotheques or bars where we have neon signs. When you take night shots, for example, you see always that the green traffic light is compromised. It's often a cyan or a blue or whatever, or it's just white. Often I get asked, where do we need really these values? I think when you cook with gas, you have a cyan light source in your house already, and you want to have it, of course, represented in the right way and not just something white. And there are many examples where you need this. So it's not just only in a bar scenario.
That's absolutely right. And I would add even further to it that from a sort of like creative POV, it's like, you know, if I look at even a more sort of conservative example of like a red brake light, that it's not as crazy as, you know, like a rave or something like that. But I might still look at that red brake light and go, well, the actual literal reproduction of what the camera saw of that as best fits on my display, that's actually indeed like too electric for me. I aesthetically, preferentially don't want to see it map quite there, but I actually can't do anything about that until it's in my gamut. So even if I do want to down map it and do like what a film print would do, for example, make it denser, make it deeper, and trim some saturation off of it, I can't begin to make those creative manipulations until it's inside of my gamut. Because try as I might, without this gamut mapping thing, the whole issue is that I don't have access to these pixels. So it's not as simple as saying like, oh, well, I don't want it to look like this anyway, so why don't I just desaturate my cyans? I'm likely not going to have any luck with that if I try it right now. It's just going to get worse.
And you will see this in Roland Emmerich's movies, Independence Day 1 and 2. He works a lot with cyan colors, and often the whole picture is just posterized it
Yeah.
it just loses details, and it's maybe on effect that he wanted to have that outwardly problem, but it looks a little bit wrong to my eye, to be honest. And so we have to take care of this. It's not just an extreme example from my point of view.
Absolutely. I completely agree. It's you need to have a smooth treatment of everything from 0 saturation to 100% saturation within your pipeline, so that you then have the creative, like autonomy to do whatever you want, whether that's nothing or everything or somewhere in between. You don't even have the option if it's not being properly mapped. Like in this case, there's nothing I can do from within this room to punch through the wall and grab stuff outside of the room unless I'm using a gamut mapping algorithm like this one.
Thank you, Cullen. You have no idea how much that means to me.
Yeah, no, it's a thing. Trust me. I was I was the one being like gaslit early on by various people, not the academy themselves. I'll be clear, but others who were like, well, like sometimes that happens, and there's no real reason or way to explain it away, and you'll just have to, sorry. Was sort of like no one had a great answer for me, so I'm glad to have better ones today.
Yeah.
Okay, Max, any other questions out there? Everyone
All good, man, in the chat.
following along? Okay, good deal.
But I just
All right,
want
so-
to point out that, we talked about DCTL before. I think for the curious audience out there, if you want to learn more about DCTL, I think you can check up 10-part series from Cullen at mixinglight.com. He has like a very nice 10-part series tutorials about writing DCTL.
Yeah, absolutely. We had a lot of fun in there, and it's a great introduction to using the tool. If anyone like follows me on my YouTube or Mixing Light or anywhere else, you know that like DCTL and coding up my own tools the way that DCTL allows me to do is an enormous part of my creative practice. So I think it's a really, really powerful thing to have the ability to work within and kind of shape your creative intent with. I'm going to, I don't know if there's a real easy way to do this, but if anyone wants to see this DCTL that I'm working with, or the initial release version of it, I actually tailored this a little bit so that I could use it. I thought it was so useful that I recreated it to work in non-ACES spaces as well, because it's not just ACES where this happens, it's anytime you have a source gamut that's larger than your working gamut. So I actually added some features to this DCTL, but the original version of it with the same core functionality is available on a public GitHub, and I'm going to paste this into our chat, Max. I don't know if there's a way to push that out, but I thought I would share it in case anyone's interested.
I can do that.
Cool. Yeah, so there's a .dctl file in there. You'll kind of have to grope your way through it if it's your first time using DCTL, but if anyone's interested, it's there to be explored.
Cool, man. Thank you for sharing.
Yeah. Oh, I didn't even see this very cool CIE diagram that you shared in the chat here, Dr. Sassi. That's a very good visual for what's happening. I'm going to see if I can actually move this over.
I think it's from Nick Shaw. I saw it in his training, where he explains how they developed the whole Gamut compression.
Oh, right. That was the one he did with Dotto, right?
Yeah, it's from the ACES PDF.
Very cool.
I hope we can just share it because it's open source, I hope.
Yes, let's see. You know what? I'm not having any luck actually pulling it into my screen share without opening into my files and revealing some client's IP or something. Anyway, it's a good visual. Maybe I'll try to pull that in later. But regardless, that's a really good exploration of the gamut mapping issue within ACES. And this is actually a great way to begin an even larger conversation about the evolution of this ACES organism that we were talking about earlier. So the ACES architecture at this point is 15 plus years old. And what there's a whole team now working on within ACES that, since they've solved the gamut mapping thing, that was the group or the thread that had my full attention for their whole journey. And Nick Shaw and some of my other favorite, like color science crushes were involved in that project. So I was following it with great interest. Since that project has wrapped up, a lot of those same people are focused on a new project, which now has my full attention whenever I'm sort of keeping pace or keeping tabs on what ACES is up to. They are figuring out how exactly ACES 2.0 is going to do its thing. And I find this very exciting for a couple of reasons. But I'm going to start by re-emphasizing something I believe we touched on briefly in our prior conversation. And that's the following. There is no such thing as a single objective, perfectly accurate color space transformation from a scene or a camera space into a display color space. I'll repeat that one more time. There's no such thing as a single perfectly objective transformation from a camera or a scene color space into a display color space. Now, that may sound like the most boring sentence that you've heard all day, but I actually found it to be kind of mind-blowing the first time I understood this idea, because I thought color management was supposed to be all about the technical, the neutral, the accurate, the non-opinionated foundation upon which I will do my creative work, right? But here's the challenge. Here's why that's true. Here's what I'm saying when I say that. Let's just kind of visually explore what I'm talking about, because I'm a visual dude and it always helps me. Let's just grab a still here. This is, again, my vanilla ACES pipeline that's taking me from what my camera saw, my Arri Alexa saw, out to what my display can show by meaning Rec 7 or 9. And I'm just pipelining that through ACES, no grading, nothing else happening here whatsoever, just that basic color management setup. Let's grab a still on that. Now, I'm going to do a rather odd color space transfer. Actually, I'm not going to do that. I'm going to do a whole different stack. So I'm going to disable all my ACES nests for a moment. So now there's no ACES happening whatsoever. There's actually nothing happening whatsoever to this image, okay? No grading, no color management. We're now going to color manage in a different way. There's a bunch of different ways I could color manage, but here's an easy one. I'm going to go to my Arri folder, and I'm just going to grab this Arri Alexa log C to Rec 7 or 9. This is the famous K1S1 LUT. And this LUT should be aimed at the exact same thing that my ACES pipeline was aimed at, fundamentally, right? Get me from Arri Alexa to Rec 7 or 9. Yeah, it's by a different mechanism. It's a LUT instead of a color space transform. Yes, it is. One is traveling through an intermediate space, the other is not. But actually, none of those things are relevant here. All that we are saying is make an objective, accurate, technically sound transform from the camera space to the display space. But let's look at what happens when we compare these. They don't agree. Well, how the hell could that be? Isn't the whole point that this is supposed to be objective so that I can do my subjective thing as an artist? Here's the reason why. Anyone who's hung out with me before has heard me use this expression. Saying I want to fit, in this example, Arri Alexa log C into Rec 7 and 9, saying I want to make that transformation, that's roughly the equivalent of me telling you, hey, you see that 10 pounds of dirt over there? I would like you to take it and place it into this 5-pound sack. How am I going to do that? I can't do that, right? All I can do is be judicious about how I pack the dirt that I can pack into that 5-pound sack. That's why we see the difference between ACES and the LUT that I just looked at, or ACES and Resolve color management, or ACES and the way that Red would transform one of their cameras out to Rec 7 or 9. It's not that one is wrong and the other is right. It's that different engineers have devised different solutions for getting the best possible reproduction of a larger dynamic range, of a higher color volume than a display can actually show, okay? So that's the foundation. That's something I think we talked about in our prior conversation, but I wanted to recap because that means that one of the core considerations, one of the biggest factors in any color management framework and in what it does to our images, whether it does good things, bad things, or okay things to our images, one of the biggest factors in there is that output transform, right? It can be better or worse. We talked about this also in our prior conversation about how the output transform in ACES has a legacy. It was originally devised as a sort of answer to the way DI colorists were working at the time, which was under print film emulations, not for stylistic reasons, but because stuff was actually going to get printed back onto film, right? So that was everyone's baseline, and they wanted to devise an output transform that would feel reasonably familiar and comfortable to that DI colorist. So as a result, the very first ACES display transforms were very film print-esque in character. In fact, Fuji helped to develop those very first ACES transforms, and they did so based on trying to get matches to certain key characteristics of a film print. That has evolved since then over the course of the ACES 0.x releases and now through the 1.x releases. But now, if we look at the ACES 2.0 upcoming release that I mentioned a couple minutes ago, the working group that is tasked with figuring out this display transform piece of the puzzle are very rightly, in my opinion, taking a step back and saying, okay, where have we come from and where do we need to go? What's the sensible thing to do with our display transform? What factors do we need to consider? How are we going to decide what the right display transformation is? And they're in the middle of that conversation right now. And it's a really fun conversation to either participate in or even just eavesdrop into, because it's all happening in the public sphere. Anyone who wants to go to acescentral.com and find the subthread for that virtual working group can follow along with the fascinating conversations that are being had about, well, is this better? Is that better? Who's going to like it this way? Who's going to hate it that way? It's a really fascinating conversation. But
what's the name of the working group, Cullen, by the way?
It is the output transform, or the output device transform virtual working group, I believe. Cool. And I've actually got a link. Or no, this is a link for what I'm about to show you. But yeah, I believe it's the ODT working group is how they're styling themselves. But you can, as I said, kind of follow along with all that stuff if, like me, you find such things fascinating. What I thought would be cool to look at today is where they are currently at with that. So where that group is at right now is they have, for the moment, narrowed down the answer to that question. What are we going to do with our ACES 2.0 output transform to 3 candidate transforms? And they're actually very different in character. They have wildly different reproductions. Let's look at our timeline level. And I'm going to go to something that I actually had pulled out when we first started our conversation. Let me go ahead and get my ACES pipeline back re-intact and make sure we're back in regular old ACES land like we've been all day. So I've got these ACES 2.0 ODT candidates over here that we're going to take a look at. So right now, let's actually just go ahead and grab a still of this too. Let's call this 1.3. This is the current ACES output transform. And then let's just flip through. I'm going to go to shot number 12 here because there's a nice range of luminance and colors in this image. And let's just flip through candidates A, B, and C. I'm going to try to make this as big as I can for y'all. Let's check out candidate A. Okay, so that's 1.3, candidate A. So that's not wildly different in terms of the vector scope. If we look at the colors and the saturations, that feels pretty similar. But what is different is the contrast feels a little bit lower now, doesn't it? Yeah. So that's sort of one variation. Let's look at candidate B. Candidate B also feels quite close to candidate A. And let's look at candidate C. This one as well actually feels quite close. And this is actually a great thing to emphasize here, guys. These transforms may look more or less similar depending on the image that we are evaluating at the time, okay? So it may be that these images all look quite close in one, like applied to one image and quite different applied to another image. But what I want to point out here that I see as the fundamental debate, the fundamental sort of like thing to negotiate in ACES 2.0 that they're dealing with is something I find completely fascinating. So let's just go back to ACES 1.3, for example, and let's just put a pin in all these candidates for a moment and just try to step inside the minds of what's being, of the working group and what they're trying to ratify here. I'm going to do this by showing an example of something. So everything that we do in motion imaging in 2022, for the moment, this is actually going to be changing, I predict, in the near future. But everything we do in motion imaging for the moment is in a 3-channel metric, a tri-stimulus metric. We have a camera that has photosites that are sensitized to either red, green, or blue light. And then everything from that point forward flows through those 3 pipes, red, green, and blue, all the way out to our display, which have red, green, and blue pixels or photosites as well. Some displays may have a white but no display has more than red, green, blue, and possibly a white. So everything is in this sort of like 3-color metric, right? And if we think about color correction, it seems perfectly sensible when we describe, well, that's the journey, those are the pipes that we run with throughout. It makes perfect sense when we talk about color correction. The default domain or realm of color correction is in that same 3-channel model, right? So when I, for example, let's say I don't think this is enough contrast here in this ACES rendering, I actually want more. The way I would do that, or a way I could do that, is to drop my lift and stretch my gain upwards, like so. Now, what am I actually doing when I do that? I am dropping, as you can see in my bars, red channel, green channel, and blue channel, all down. And with gain, I am pushing red channel, green channel, and blue channel all upwards, okay? Here's a fascinating thing that I only quite recently learned. This is not just manipulating my contrast. This is manipulating 2 other things, just simple contrast operations like this. It's manipulating 2 other things. It's manipulating saturation. Most of us have probably noticed that, right? Like, look at my vector scope. It's actually expanding just because I did contrast. I didn't add saturation here, but it's changing saturation, right? But the other thing that is maybe a little bit less noticeable, but you can see it when we point it out, it's actually changing hue. The hue of my image is changing, right?
Wow.
Yeah.
Wow.
And this gets worse. If you look at, this is just a little nudge. Think about a big, fat, massive manipulation like this one. That's massively shifting your saturations and your hues. Now, I will make this caveat. This is exactly, well, not exactly, this is in alignment with the way a film print functions. And some of what we are seeing here is not necessarily problematic, okay? Some of it is actually aesthetically pleasing, or at least something we are aesthetically conditioned to accept. However, this is not the place to get that sort of preferential thing, if that's indeed what we want. We need to find a better solution to this, because just manipulating RGB, just trying to tone map in RGB, which is like the biggest thing that's happening here. We're moving from log into a display gamma state. Doing that, operating directly on our RGB channels, is shifting not just tonality, but saturation and hue. And I don't know about you, but I find that incredibly, like, mind-blowing that that's a thing. And that's the way that all color management frameworks today work, is they operate directly on red, green, and blue. And we all just accept, yep, it's going to shift my primaries around. So just to put a finer, like, sort of demo on it, I'll give you this sort of rule of thumb. If I'm doing a custom curves operation, again, you can be a Resolve user or not. This should be fairly intuitive to observe. If I have a pivot point somewhere around here and I just want to do like a traditional S curve, let's like walk through what's happening here. Any place where I drop below my original unity line, I'm going to be increasing saturation, and my hues will collapse toward my primaries. So near red will stand straight up increasingly and start to become pure red. Near blue will start to drop pure, move off to the east there and become a very, very pure aligned blue, okay? That's what happens when I drop below, when I add contrast in the bottom. When I go above, exact opposite's going to happen. I'm going to lose saturation. The image is going to become more bleached in the top, and I'm going to collapse my hues or my primaries toward the secondaries, okay? So near, in this case, like if we're looking at our skin tone line, for example, in this circumstance down here, a hue that plots right here is going to move toward red. In this circumstance up here, a hue that plots right here is actually going to move towards yellow, okay? So we're getting all this wild hue shift, which again, like, that's actually something that may ring familiar to any of you guys who've studied the way that filmic rendering sort of works, the way that film prints render images. Film prints have, like you'll hear people talk about the sort of like bleached or desaturated highlights of a film print. That's why, because you're operating on the 3 channels. In that case, it's cyan, magenta, and yellow. But the same concept applies. You can't, you are, as you are increasing the gain, or, like pushing the signal up here, you're going to lose saturation and your hues are going to collapse from being more primary toward more secondary. So that perceptual saturation is going to be even greater as a result, okay? So that's the idea there. So the reason I mention all this is because for the first time, ACES are now contemplating, well, in our rendering, are we going to do candidate A is what they are calling a simple RGB mapping. So it's the closest to what we currently have. It's the least radical departure from what we currently have. Candidate B is what they are calling a hue preserving tone mapping. And I'm not confident that's actually applying there because I'm not seeing the change I would expect. There we go. So can you see look at my vector scope between candidate A and now when I apply candidate B, it's quite different, right? You can see it in the scopes. You could even see it somewhat in the image, and depending on the values that you were looking at, it would be even more prominent. But we can see when we compare these things side by side, they're the same transform aimed at the same thing, but those little shifts, I mean, if you're doing what I do for a living, concerning yourself with the fine nuances of the way a final image is rendered, that's a huge deal. That's a huge shift. If I set a look with my client here and we all sign off on this grade and we show up to start work the next day and it looks like this, I guarantee you we're all going to notice and go, where the hell did my image go? It's a big difference. It's a big change. So these are some of the fascinating conversations that are being had in the public eye in that virtual working group on ACES. And all this ends up being what I see as just kind of a fun diving board for getting a better understanding of image science and how it affects the creative concerns of image reproduction and like motion imaging in general. And those conversations all just happen to be having had out in the public eye. Now, one more thing that well, actually, I'm going to take a breath because we talked about a bunch of stuff there. How's everybody feeling? Questions you guys want to clarify or anything coming from our viewers today?
It's fine, and the viewers, it's quiet.
Awesome. Okay, so here's the sort of other side of that coin that I find almost as fascinating as basically I'm taking a long way of suggesting to you guys that, well, if we want to be accurate, if we want to preserve our hues from their scene state and our saturation from their scene state without sort of artificially or arbitrarily shifting those things, we should be using a hue invariant type of tone mapping. And I'm going to show you what that looks like now. And also show you why being hue variant may actually still be advantageous in a creative context. We just don't want to gum up and confuse the creative and the technical, okay? So let's say we are using candidate B, which is our new handy hue invariant display output, okay? I'm now going to go over to my clip level. Let's take a look at this little still that I've prepped here. So all I have here are two nodes. Node number one is good old RGB, which I'm going to manipulate with some basic contrast. So you can see I'm working my panel, but you guys can see my contrast field here is increasing. Let's go up to like 1.25, like so. Okay. If I flip that off and on, I'm getting that extra hit of contrast. It's doing all the stuff that I just talked about. You can see right here, look at these primaries that are like standing up as I increase that RGB contrast. Let's go over here to this node. This node is different. This node, instead of operating on my red, green, and my blue simultaneously, this node is doing a little bit of fancy footwork under the hood. Before it exposes my controls to me, the colorist, what it's doing is saying, hey, take RGB and calculate luminance from RGB. Now, there's a number of different ways to do that, and that will affect the way that this next step works. But there are a number of sound ways or reasonable ways to say, hey, if my RGB is, like XYZ, ABC, whatever that triplet is, what's a good formula for calculating luminance from that triplet? There's a good way to do that. And then you can operate on that luminance channel as opposed to directly on your RGBs. And I just want to, we don't have to follow every twist and turn of that to enjoy what comes next. I'm simply going to do a symmetrical amount of contrast reduction here on this node to what I added here in this node, okay? So I added 25% contrast here. I'm now going to reduce, I'm going to take my contrast back by 25%. And because I suck at math, I'm actually going to confirm that I'm doing that correctly. What's 1.25 times 1.25? No, I'm overthinking that actually. We just need to do
0.8.
Yeah, thank you. Thank you. Okay, so we've done 1.25 and then we've done the exact opposite of that contrast. So we should be seeing no real net change in actual the contrast of our image's luminance, if that makes sense. But what we do have here that I find fascinating is actually a really beautiful form of saturation. That's one of the reasons why we've gotten away with this insanity for so long, is because aesthetically it's actually kind of pleasing, at least in some contexts. Like, let's consider this for a moment. If I treat this stack, these two nodes, as nothing but a saturation adjustment, because that's effectively all they're doing, like so, yeah. Is that, am I crazy? Should that be 0.75? It's a little bit tough to.
When you put 25%, you have 125. When you take then 25 from 125, you take more than 25 from the, as compared to the original.
Uh-huh.
Makes that sense?
Yes. So does that mean we should be at 0.8?
I would think so.
Yeah. See, one of about 5 times a week when I go, gosh, turns out I really should have been paying attention in math class, because I'm now having to relearn it as a grown-up.
Make it counting by fingers. We have 4 fingers. Each is 25%. We put 25% on top, then we have 5 fingers. To have 100% back, we need only 4 of them. Since 125 is 100, it would be 80%. I'm
so glad you're here, Dr. Sassi. I just saved myself a world of trouble. That's great. And it gets, of course, even more difficult because we're, you know, like we're having to deal with perceptually what is zero contrast, but you're absolutely right. So if we look at this stack as we've just now confirmed that we are not affecting any change in contrast, all we're doing is, you know, what I would expect of like, well, when you manipulate RGB, you're changing your hue and your sat. When you manipulate a luminance channel, you are not changing your hue and your sat, you're only changing your contrast. So when I apply X amount of contrast here and then take that same amount of contrast out while operating on an L channel, we can conclude from there that all we're doing is altering our hue and our sat, right? So let's grab a still on this and disable these for a moment, and then compare this with adding a sort of arbitrary amount of saturation with the saturation knob. So if anyone's thought about subtractive saturation or filmic saturation or heard those terms thrown around or wondered how they can get more filmic saturation, we are indeed getting a much more pleasing, by my eye, form of saturation from this sort of like indirect introduction of it that we are getting over here than when I twist my saturation knob, which I find kind of fascinating, and I think is the reason why this, you know, like hue shifting, saturation shifting property of RGB tone mapping has gone unchecked for so long, because most of the time it looks really good. And we've got a sort of precedent for it in the way that film prints treat images, because they also don't leave hue and saturation unaffected. They manipulate it like crazy. So the manipulation is not always bad if it's what you want, but I would argue you need to be able to decouple those, at least to audition that. And that's where something like Candidate B in ACES 2.0 is going to come to the rescue, because we can have that solid foundation. And then on top of that, just to the extent that we want to, we can do something like this. And this is, you know, like, again, you don't need to understand everything about what I'm doing. But if I look at, let's see, let me go back into this for a moment. If I turn this into just a thing, doesn't matter how I got it, it's just a thing I can turn up or down, I can now effectively have my more pleasing form of saturation here. Okay, so this would be like, here's just my hue preserving color management, and here is just preferentially introducing some of that more tasty saturation that you get as a byproduct, as opposed to standard video saturation like we have here, which tends to do very garish things, especially with medium to high saturations. So such are the things that I find fascinating, not only from a technical POV, but from a creative POV. Any questions on any of that stuff? Anything that you guys want to talk about?
I mean, I'm following along, so if I'm following
Awesome.
along, that's an amazing sign. Like even like the Hue Invariant stuff was phenomenally interesting.
Yeah, it's pretty cool, right?
Yeah.
I'm going to give you guys a couple of links. If you want to check out these, you've now had your, some of you probably been introduced to DCTL for the first time here today. If you want to check out these candidates for yourself, they're all out there, freely available. I'm going to paste that link into the chat, and Chad can share it with y'all. And you can go in and, like what I'm actually looking at here is like, hey, we're looking at the, revision 9 of the ACES 2 candidates, candidate A, candidate B, candidate C. And right now they just have 2 display spec targets. We've got Rec 2100 or Rec 709. I'm doing Rec 709 for all of these. And I think it's really fascinating to look at. And I would argue, for any of us who are working in motion imaging, I don't care if you are on set, I don't care if you're a visual effects artist, I don't care if you're a colorist, I don't care if you're an editor, we should all have some bearing as to the journey that our images are being led on, and have a sense of like, is that a really good, really optimal, really efficient journey that yields best visual results? Or is it something less than that? And how can we constantly be moving toward that more optimal version of it? ACES is a leader in that space. The conversations are being had in public, and there's no reason we can't be all a little bit more in the know and educated about where it's at, where it's come from, and where it's going. And in doing so, feel more empowered to apply our craft and to understand, okay, what I do is not just this narrow one thing that I do. It's everything that happened leading up to my work as an editor or a colorist or a VFX artist, and it's also everything that's going to follow that work, as we talked about right here. Because if I, easy example, if I'm looking at the, like my grading decisions are going to change under each of these intents, right? Like even to look at a more dramatic version, if we go back to our Alexa LUT, even though these are both theoretically technically sound transforms, at least once I turn this off, they are, my grading decisions are going to change based on each of these. So I want to have the proper context, and I want to have the ideal pipeline in place so that I can make the best grading decisions and get the best version of my image as quickly as possible. So this is the deep end of the swimming pool, guys. We started off by talking about, well, gee, this seems pretty simple. We just need to take what the camera saw and turn it into what the display can show. And shouldn't there be a framework that's well supported and open source and regularly updated that helps us do that? Seems so easy back then, doesn't it? It's like, yeah, cool, make that. Oh, cool, someone made it, awesome, I guess I can use it. But there's more than one group or organization making it. It's an evolving standard. There are more than one set of needs out there. There's more than one opinion. My favorite thing about that thread that I'm talking about on the ACES working group is there are people arguing passionately for both sides of this Hue Invariant versus Hue Variant display transform thing. It's not an open and shut case. It's not like all of a sudden someone figured this out and everyone went, oh my God, I'm so glad you figured this out. We have to do it this way now. It's being contentiously debated right now. So that's a debate that I'm really glad is happening in a constructive sphere among smart people, and that any of us can be party to it and even get involved in it if we so wish.
We're witnessing a history in the making here, right?
Yeah, absolutely. And this is the stuff, this is a history that this kind of history has always been in the making, as Max is saying. Like, if we look at the history of film, this stuff was always happening behind closed doors at Kodak and Fuji. Hey, what's the next generation of print stocks going to look like? How can we improve on the prior generation? Those conversations were always being had. The only difference was that they were being made by a very small group of people in a private context. And now in the digital realm, it's being made by a larger group of people, and it's in a public context, and we all get to at least see what the conversation is, and in a lot of cases actually participate and help shape its results. So I think it's an incredibly exciting time, and one of many reasons why, as much as I love film and I talk about film emulation and the beauty of traditional photochemical systems, one of the main reasons why I'm so excited to be practicing my craft today and not 30 years ago or 50 years ago, because we have far more control and ability to sort of understand how our image is traveling from light hitting a capture medium to light hitting our eyes, and to actually play a creative role and an authorship role in shaping that journey, as opposed to being like, well, it looks pretty good, which is a good thing because I don't have a say in how it looks. It's a much more empowered position that we're in today. And I can't believe that we covered all that in this amount of time.
Wow.
That's the bottom of the rabbit hole, guys. That's where we're at with ACES.
I really need to, I really need to rewatch this to understand this, right, Cullen?
Yeah,
I'm definitely going to rewatch it.
There's a lot to it, right?
Yeah.
Yeah, I mean, any thoughts, questions, things that you guys had to add here?
I did have that quick question about. Oh, sorry, Dr. Sassi. I was just going to say
go ahead.
The ACES CCTCG.
Oh yeah.
Is there a quick, easy explanation for that, or is that kind of just has to be a bigger conversation that we don't have time for?
No, there is a quick and easy explanation, and I'm glad you reminded me to return to that. So I want to simplify that, and that's another thing I feel like we can all, if you don't follow every twist and turn of everything we talked about today, that's okay. You're not going to lose your job. However, something we should all walk away with when we finish this conversation today is a completely unambiguous and simple understanding of ACES CCT, ACES CZ, ACES CC, ACES CG, and ACES. There's 4 color spaces that are sort of like color spaces that belong to the ACES family, okay? The easiest way to understand these is in terms of their component parts. So we're just going to do a little bit of kind of color space 101. Any color space is going to be described by 2 things. It's going to be described by a tone curve. That tone curve would be something like a log curve or a linear curve, which we discussed earlier, or a gamma curve in terms of like the color space of a normal SDR display. It's going to be a description of how that color space responds to a particular stimulus. So linear light would be the simplest. That just means if I show you a patch of 18% gray and you meter it as 0.18, and then I double the amount of light hitting that 18% gray patch, so now double the amount of light is coming off of it, that means that you're going to read 36%, 0.36, because that's double. That's a linear response. It gets more complicated with other tone curves from there, but that's the basic idea. It's just describing the strength of stimulus relevant or relative to the strength of response of a camera sensor or of a display. Okay, so that's a tone curve. That's part number 1 of a color space. Part number 2, we spent the first hour of our time today talking about. That's your gamut. That's your primary set. That's that triangle on the CIE horseshoe. Those 2 ingredients, tone curve and primaries, are what are needed to describe any color space. And so all 4 of those color spaces that we just rattled off, ACES CC, ACES CCT, ACES CG, and big boy ACES, or just, like the full-on ACES, those are the components of each of those color spaces. They have a tone curve and they have a primary set. Now, the reason I take the time to emphasize that up front is because there's actually only, those are all just variations on a couple of factors. So you have 2 options for your tone curve and 2 options for your primaries, basically, in ACES. You have your linear tone curve, and then you have your log tone curve, okay? Now, technically, there's 2 slightly different flavors of log tone curve. There's CC and CCT. They are virtually identical. They're so close. And CC is almost deprecated at this point. No one's really using it for reasons that may indeed be beyond the scope of this conversation. But you can be satisfied to know that there are 2 tone curves. There's a linear and there's a log curve. The log curve we call CCT. There's another variation on that log curve that really isn't much of a factor these days. Same thing with our primary set, or with our gamut. We're probably all familiar with what our 2 primary sets are now, right? We have AP-0, which, as we observed, is almost identical to the XYZ color space. And then we have AP-1, which is almost identical to the Rec 2020 primary set, okay? Those are our 2 primaries. So those 4 ingredients, linear or log, AP-0 or AP-1, are the foundation of all of these different color spaces that we're talking about within ACES. So ACES, just plain the ACES color space itself, that is AP-0 primaries and a linear tone curve. That's all it is, okay? ACES CCT, that is AP-1 primaries and the log tone curve, specifically the CCT tone curve. ACES CC, this is again the least important one that we have the least need to understand. That's the same thing as ACES CCT, but with that very minor variation in the log curve that I just mentioned that really isn't worth going into much more detail right now. And then the final one, ACES CG, that's the only combination that we haven't talked about yet. That is the AP1 primary set with a linear response. And we actually had a great conversation in the first part of this two-part series where we talked about the exchange with visual effects vendors and how some VFX vendors may want AP0, or rather ACES, like the full AP0 linear as their exchange format. Others may be perfectly content to receive ACES CG, which is also linear, but it's got that smaller AP1 primary set as opposed to AP0. And again, just to put visual at least to those primaries, we've got our AP0 over here, completely encapsulates this horseshoe. And then we've got our AP1 over here, which pretty tightly traces the Rec 2020 primary set. So those four standards are all variations on that same finite set of tone curves and primary sets that that ACES has standardized. Does that help there, Chad, you think?
Thank you. Yes, that's fantastic. Thank you so much. Sorry, Dr. Sassy, go for it.
Yeah, I had something I wanted to say. Thanks to Carl Beery, I hope I pronounced his name right, and he mentioned Photoshop with the RGB theme, and that is what I normally do when I have a curve on top of an image, that I instantly put in desaturation on top of it as well to get kind of back where I want it to be. So saturation being the difference between two of the colors. The larger it becomes, the more saturation you have. And thanks for the example, because I just wanted to say it and then I saw it. Yes, perfect.
Yeah.
What I want to stress out a little bit, in 2008, when the ACES people came together to finally get 200 experts to create ACES, which was then in 2012, finally in a paper, there was no CC, CCT, or ZG. All of that came together from my point of view, and maybe you correct me here, because I run often into problems when I communicate in this way, that application with the code that they had at that time couldn't handle AP0. So it is a compromise to get from the full color space into a smaller color space with all the problems that it has. And after a while, people got so used to use CG, CC, CCT that they say already, this is a specialized format, it's perfect, and all of that. From my point of view, it's as before a compromise, and I hope that all the applications, if it is Nuke or Fusion or whatever, who has maybe problems to a certain degree, can finally handle it 100%. And with Fusion, I asked the support at Blackmagic. They said normally you can feed ACES 26.5 into it. And so I'm sometimes uncertain what is really working, what is not. And the second point that I wanted to make is often people decide from a display what is needed and wanted while they don't have even calibrated that display and have maybe the brightness set to something that just fits their comfort zone. And so there's a huge idea of we decide something, as you said, I need to punch through the wall to get to the outer space, what was artificially limited by a wall. And to say my room is small and that's all I need is the wrong idea from my point of view. And do you have something to add?
Absolutely, yeah. I'm really glad you emphasized those points. It's something, frankly, even I forget. You know, computing itself and software, like in terms of processing power, have come a hell of a long way since, you know, like 2008 or even 2012. And my understanding is exactly as yours is, that part of the sort of notion behind that AP1 primary set is that requires, you know, like less of everything. When you've got a smaller gamut to contend with, it's an easier proposition for a piece of software to work with. Absolutely. So I'm glad you emphasized that, because I frankly had forgotten about it.
Thank you.
Yeah. And
thanks for the support.
yeah. No, and I mean, it's funny too, like something that I haven't even touched on yet is that when I started, like I stressed before, this whole hue like shifting RGB thing that we talked about before. When I heard this, I was like, wait, really? Like, really? That's a thing? I had difficulty accepting it. And I'll tell you, when I actually started to accept it was when I started to look at the compensations that were being made to account for this in published literature from the ACES committee, from ARI, where they actually will tell you, like, here's an easy example. The matrix that transforms you from ARI-wide gamut to Rec 7 or 9 that is sort of cooked into that K1S1 LUT that we looked at a little while ago, that's actually not just a perfect technical matrix. It has a saturation reduction built into its diagonal axis. So if you take a matrix and you reduce your red and red, your green and green, and your blue and blue, you end up pulling out saturation from the image. There is a subjective compensation for the saturation added by the tone mapping in that diagonal row so that you're getting a net of what the area engineers felt was a more balanced, less oversaturated image. Same thing with ACES. There's a factor, there's a process in the ACES reference rendering transform or in the output transform that is aimed at specifically reds and sort of bringing down screaming hot reds that are a partial byproduct of that RGB tone mapping. So it really is a thing, and it's fascinating to realize, like, oh, okay, we've actually known about this for a while, and there actually have been reasonable compensations made. But of course, from a science point of view and a practicality and a purity point of view, the best compensation is the one that you don't need to make, right? If you can figure out, well, this is my whole beef with the phrase, to go on a very brief tangent. You hear the phrase color correction thrown around all the time. The truth is, like, it doesn't really matter what you call it. Color correction and color grading are performed by the same people in the same software. So what does it matter what you call it? My problem with the language, however, is the idea that images need to be disciplined. And my question is, like, why are they incorrect? And if they're incorrect, can't we do something to remedy that at the source as opposed to downstream compensating for it? So that's a great example to me of, like, if you're having to make an alteration to your technical matrix in order to get a reasonable output from it, that's a good clue that you probably are doing something that could be optimized in a different way. A tangent, but relevant to what we're talking about.
Yeah.
Gosh, what else? Any other questions? Anything else you guys think we should talk about?
Can you explain the difference between tone mapping and gamut compression? Some people use it interchangeably, and I think there's a problem when you do that.
Yeah, I definitely agree with you, and it's understandable why those things get used interchangeably in some cases. Let's go back to ACES here, because they relate to one another. But the easiest way, the way that I tend to think about it, let's party for a second. You guys want to party?
Absolutely, man.
Let's party.
Yeah.
So we're gonna visualize this thing. I'm always obsessed with, like, talk is cheap. Show it to me.
Yeah, show and tell.
Yeah, exactly. We're all, probably everyone in this room is a visual person. So let me just spin this up very quickly. We're gonna actually look at visually what the difference is between these two ideas. So tone mapping is really just a fancy word for messing with your RGB channels. Like, it can be sort of subjective and creative in nature, or it can be done with a color space transform. It's doing the same thing. It's doing what we've talked about several times today. We're just operating on our red, green, and our blue channels. Okay, so, like, let's actually make a quick tweak here. I'm going to align these so I'm seeing a change in both places. And let's actually get a display transform on the image so that it looks somewhat reasonable.
What you set up at the moment is pretty much an A/B from two different passes.
Exactly. So we're going to now get to look at the same process as it affects my image versus as it affects a Unity RGB cube. So with nothing on here right now whatsoever, you can see I'm looking at a 3D visualization of my red, green, and my blue. So here is 0, 0, 0, meaning pure black. Up here on the other end is 1, 1, 1, meaning pure white. And then everywhere in between is just colors. So this is the red axis. Over here is pure red, 1, 0, 0. Over here is pure blue, 0, 0, 1. And up here is pure green, 0, 1, 0. So I've got these coordinates. And then I've got cyan, magenta, and yellow in play as well. But it's a handy way of visualizing what's happening, and we're going to see why. So let me get this thing to behave itself. There we go. So I was beginning to draw a curve and use it as a way of describing tone mapping. So this is not the prettiest curve I've ever drawn, but it makes my point. Like, okay, we're now all familiar with what happens when we start manipulating the tonality of our image, when we start manipulating the red, green, and the blue channels of our image, right? I could do this with curves. I could do this with a color space transform. I could do this with lift, gamma, gain. It doesn't matter. All I'm doing is in isolation, messing with the red, messing with the green, and messing with the blue channels. And the one thing I can't do with this color curves thing is affect the relationship between the red, the green, and the blue. So for example, I can't say, let's add a little bit of green into my red. I can't do that here. I would have to use another mechanism in order to do that. So because I can't do that, because everything is confined to its lane, this is what we typically call a 1D transformation. And we can see that one line being represented here. And you'll notice here as well, that's having a fairly limited effect on my cube. Like you can see that the distribution within the cube is changing, but the overall shape of the cube is not changing, right? Nothing is really happening there. And so let's compare that with gamut mapping. Let's actually just look at that gamut compression gizmo that we were looking at a little while ago. This might look a little bit weird, but it's going to make our point. If we start to mess with the points of this gamut, we are doing fundamentally more complex stuff, right? We're actually manipulating the cube itself. We are manipulating its geometry. And this is just one handy example of any multitude of ways that I might start to manipulate the geometry of my cube. You know, like another easy one would be if I am in, I could do a curve like this on my saturation, and in doing so, I could effectively begin to kind of map my gamut. So you don't have to follow along with this part. I'm just going to get myself into a proper model, like so. Let's see here. There we go. So let's do like HSV. That's going to be familiar to most of us. That's actually a pretty cool visual right there, isn't it? So if I now take this same exact curve that I was working with before, and I limit it to operate only on, I'm going to actually reset this, and now we're just going to work on our green channel, which is in the world that I'm in now, in the room that I'm in now. I am manipulating saturation. Check out what happens to this cube. Let's see here. That's good. That's good. Oh, I just need to get my instance pasted up top so that the image is doing what the cube is doing. So again, pay no attention to the red man behind the curtain. You don't need to follow all this insanity that I'm doing. What's important is that I can now get a nonlinear mapping of my cube. Okay, I can do all kinds of interesting things with this cube because I'm manipulating not the red, the green, or the blue, but the saturation. Okay, and just as one more example of something that is a three-dimensional manipulation, not a one-dimensional manipulation, let's look at a matrix. So this is like where we were, let me turn this off. This is what we were talking about earlier with color space transformations. Maybe I'll disable these for now. I can actually affect changes along these axes. I can actually skew things in all kinds of interesting directions here which I never could have done with my primaries. Okay, no matter how hard I try, I could never get those primaries to do what I'm doing right now, which is actually skewing and, you know, like changing the shape of this cube. This is a form of what we're doing when we apply a matrix as a color space transformation. But to go back to the original question, the realm where we're actually changing the 3D model of the cube, where we're actually changing the shape of it, this is the realm of gamut mapping. Gamut mapping is a 3D proposition, as opposed to tone mapping, which is a 1D proposition. All that we are doing is linearly controlling one or more channels. We may be operating on a red, green, and a blue simultaneously, but it is still one-dimensional in the sense that we are not defining relationships between those things. We're not creating interaction between those things. We're just doing a thing to one channel, a thing to another channel, and a thing to a third channel, and they have no idea what one another is doing, if that makes sense. So it's essentially a 1D versus a 3D difference, is the difference between tone mapping and gamut mapping.
Yeah, and sometimes tone mapping is seen just as an overall, all RGB values are adjusted in the same way. It's just so you avoid the clipping, but you don't do anything to the colors, and there problems arise. And maybe I want to add that the term tone mapping has gotten a bad rap during the HDRI time, where everyone took HDR images and locally tone mapped them. So you got these false colors nearly, these totally blown out, all hyper-saturated stuff. This is not what we are talking about. It's more the global tone mapping. And it's a complete different beast and different technology. But I'm happy that we have gamut mapping.
Absolutely. And it's, you know, like worth emphasizing as well that like the answer to that question of like, you know, Cullen just told me to take 10 pounds of dirt and fit it into a 5-pound sack. The answer to that question is tone mapping. That the only way that you get anything reasonable is with tone mapping. I mean, check this out in my color space transform. If I turn that off, things are not very much fun in my highlights anymore, because I'm just going to keep climbing and climbing and climbing off to infinity. And I'm not making any accounting for the fact that maybe I want to put these highlights at, you know, 1,000 nits. That's all good and well, but my display is not going to climb that far. So all that's going to happen is that signal is going to crash into the ceiling at 100 nits, and it's going to be a horrific reproduction. So tone mapping is how we get that fit into what our display can show, which is actually the same way gamut mapping works. It's just in a 3D versus a 1D model.
Well, amazing.
No idea. Yeah.
It's very visually, how do you call it? Very helpful to see this visually. So thank you so much for showing that, Cullen.
Yeah, no, of course. I feel like I'm glad you feel that way. Whenever so many of these things I struggled with for years, until someone who actually knew the things and didn't just want to sound smart said, come here, take a look at this. Let me show it to you. And once they did, I went, oh, that's easy. I may not be able to do all that math right now, but I understand the concepts, you know, like, because we're all visual people, right?
Yeah. And by the way, go on, Dr. Sassi.
Since we went so fast through the main body of work today, I like to add something. We as a company, Maxon One, have different products, and most of them, or pretty much all of them, are just virtual. So we don't have really something where we can say this is now the maximum that the camera can do. In Cinema 4D, for example, we can put in all kinds of values, maybe 100 times even of the strength. This leads to the point where I feel always uncomfortable when we just do something inside of that virtual space and then toss it into ACES. The point that I try to make is the gray card or the white card. There is a definition how we produce something so it is comparable, because we have no input transfer function for anything CG or ACES 26.5 when we just virtually produce it. And that point is something I would like to stress, and maybe you have some thoughts. What do you would like to have as a colorist when someone comes with animation and wants to have it color corrected or color graded? Do you want to have it on a gray point 0.18 or 0.319 for log, if I'm not mistaken? Is that something you require, or do you say, okay, bring it and I will adjust it?
Yeah, it's a great question to ask. And my answer for physical production is maybe a little different than the application you're talking about, although there's going to be some overlap. My answer with physical production, this is, I tell this to my clients, my color grading clients all the time. I say, like, how like what I can do for your images, the lengths that I can go to for your image is pretty directly tethered to one simple question. Did you middle expose what you intended to? If you did, then we've got all the room in the world to sculpt things around that anchor point. If you didn't, the further away from that ideal that you are, the more time we're going to spend just trying to get things where they belong. And once we do that, the less latitude and room we're going to have to, you know, easy example. If you underexpose by even a half a stop, that means that the first thing in my adjustments is going to be to compensate for that, because you don't want the exposure to sit there. You want it to sit a half a stop higher. But that means I've now stretched out your distance between your middle gray and the floor of your sensor. So I'm going to see noise sooner. I've got fewer discrete shades of gray in the actual negative to work with. So my ability to like sculpt the bottom end of your image, for example, and make it really, really tasty and beautiful is going to be compromised even by that half stop difference between what you thought you were exposing and what you actually exposed. So I think the same thing applies. Like, we want to have, you know, especially when we're using log curves, you want to be targeting the sweet spot of that log curve. So if the manufacturer says that's 0.391, as Dr. Sassy says, then that's where you want your middle exposure to encode in the camera. And probably the same thing with, you know, like virtually generated assets, unless it's all staying linear anyway, in which case it may be a slightly less of a factor. But if it's any point it's going to be turned into a log curve, or if I'm going to map it into a log curve even, I want to make sure that I'm mapping it into the proper position within that log curve so that I can make adjustments anchored around that without having to start with a compensation. Kind of goes back to that conversation we had a few minutes ago of the best compensation being none at all. So if you can have a system that requires, you know, even in this virtually generated asset, if middle gray is parked where you want it to see, which by the way is not a technical consideration, I might want to middle expose in this image. I might elect that my subject is, you know, like these flowers over here, these plants, or this bowl of fruit, or this mirror. Like, I can choose my subject wherever I want. It's just that once I have, that's what I should be prioritizing middle exposure. So when you have a virtually generated asset, you simply have the same principles in play. You make sure that the proper, significant subject is middle exposed, and then at a baseline, running that through a sensible, accurate pipeline, you will have a balanced image state, if that makes sense. And then all we get to do is have fun around that, as opposed to figuring out, like, gosh, why does it look so dark? And now that we've adjusted for how dark it looks, what room is there left to do what we really wanted to do in the first place?
Yeah, I think you mentioned it with a LUT that you have produced for exactly that client who underexposed for a half stop, that the LUT is produced exactly for that shooting, and it would not work when the shooting would be correct in that.
Yeah.
way.
Yeah, exactly. The idea there is, like, you know, I know some of my favorite cinematographers still light by meter, which is a great idea, but to the extent that your meter and your camera see the same thing, which is the assumption that you're making anyway when you use a meter, your camera is a meter too. You just need to get it to tell you what it's seeing. So that's the whole idea with this LUT that I'm talking about, is it's just telling you, hey, right now, while we're live, while we're here on the set, here's what I'm encoding as 18% gray. You may think it's this, but it's actually that, or it'll confirm for you. Nope, you're nailing it. Hit record, you got it locked in, you know? So just having that, you know, so much of what we do is about having proper context to make good decisions in.
I was just looking if I find my spectrometer and hold it in the camera to lead to another question. When you said light meter, of course, both Sekonic are needed from my point of view, because the camera is always trying to find a middle average what the camera sees. But you can't just hold the camera somewhere else and then shoot again and try to get your color temperature. Do you prefer the data that someone would get from set with the Sekonic C800, for example, which is way more precise than any camera really can give you that, which is metadata most of the time. Sorry.
Yeah, no, it's funny. I actually don't know what the explanation for this is, but I can tell you that every one of my cinematographer clients who uses something like that Sekonic meter, they bring me better negative. Now, whether that's because they are being given better context or simply because they are by definition being more careful and mindful of what they're doing, I'm not so sure, but I definitely see a positive correlation there. Like if you're metering and taking the time to make sure you're exposing consistent with your creative agenda, that I always see the difference when that material comes in. Like, wow, these exposures just are sitting in the right place, shot after shot after shot.
And by design,
especially when you have.
I just want to add a little bit that, by design, the light meter and then the meter on your camera is like totally two different metering system, right? One is like the incident meter, and the one in your camera is like spot metering system.
Yes.
You have normally both. You have that little look through, and you have a dome on
exactly.
cinematographer.
But the camera doesn't have the incident light meter.
Yeah.
And there's another. Sorry, go ahead, Dr. Sassi.
Very quick, and sorry, I'm getting so excited about.
No
this.
problem, man.
It's exciting.
Typically, when you have your light meter the first day, you calibrate it to your camera, so the light meter really knows what the camera is doing on the sensor. Yeah. It's not that you can just put both in a case and you're done with it. You have to match these, and in the moment your light meter knows what the camera really can produce, you get already better results, and with the curve that you plot how much dynamic range you really have.
Absolutely.
Sorry to interrupt.
No, not at all. I mean, the only other emphasis I was going to make is that a light meter and a camera actually have sort of fundamentally different agendas as well. A camera is trying to make you like what you see. A light meter's only value is in its accuracy. No one cares about a camera that's accurate if it doesn't produce good images. And conversely, people are unlikely to complain about a camera that has some geeky technical inaccuracies if the images keep looking good, So that's why it's so important to figure out how to align, like the metric of one to the other, so that if the light meter says you're doing what you think you're doing, that means that the camera is seeing that same thing. Because as you say, it's not a default thing that you just get for free.
Right. Well, while I'm having one eye on the clock, I think we are reaching, the limit of our time here, Cullen. I could sit with you and talk about this like the whole weekend, man.
I know. I'm really excited. I feel like you guys we had a great group today that really followed along, and I'm really glad we got to kind of do some bonus round stuff in addition to solving the mysteries of ACES.
Amazing. So, guys, if you like what you're seeing today, and if you want to dive deeper, I really highly recommend it to check Cullen's masterclass that available in Tech Resolve training, and I think I already paste the link in the descriptions. So, where else can we find you, Cullen? I think I heard you have a YouTube channel, right?
I do have a YouTube channel. That's a great place to find me. That's where I am most active and most regularly, like posting new content. So that's a great place to see what I'm up to and to connect with me, and honestly with a bunch of other my community that are with me on that channel are some of my favorite people in this business. So it's a great place to connect not only with me but with a really great community of passionate image makers and post professionals.
Amazing. Carl just mentioned, see you in the great school.
Yeah, that's right. We do our live sessions kind of like this one ended up being for the last 15 minutes, where we just kind of riff and talk about interesting things. We do those every Friday on my YouTube channel. So that's usually a pretty good time.
All right. Amazing. So make sure you check the recording for this session as well, guys. It will be available in Maxon Training Team YouTube channel under the name Maxon Training Team. So, of course. And don't forget to get your free t-shirt as well. That's the link is also, I think it's available in the chat as well. So with that being said, Cullen, thank you very, very much for the session today. It's amazing.
Seriously.
Thank you so much for the knowledge
You're very
shower.
welcome. An absolute pleasure, guys. I loved hanging out in our first talk, and this one was even more fun, I feel like. So I hope we get to do it again.
Yeah, looking forward for the future sessions, man. Amazing.
Yeah.
Take care, everybody, and enjoy your day. Bye.
Have a great day, everyone. Bye-bye.
Yeah.